So we're not electrical engineers, we're not neuroscientists, but the whole idea of what we're trying to do is de-black box. Are you familiar with that term?
Mm-hmm.
Or just
Absolutely.
unpack this
Right.
technology. So I want to ask you to just like
Explain it in layman's terms.
No,
Okay.
the opposite. I want you to like don't go easy on us. Just
Okay.
give as much detail as you're willing to give out on the process from brain to prosthetic back to prosthetic.
Okay, sure.
Yeah.
Okay, so we don't have enough time to
Right.
do all that.
That's
So
fine.
let me kind of just explain, kind of from a high level how it works, and because any one of these things you can go into a lot of detail. But when you think about moving your arm, okay, the areas in your brain, there's an area of your brain called motor cortex. Okay, and that area of the brain is involved in actually moving muscles. Okay, so and they're very specific areas of the motor cortex that are associated with the fingers, the hand, the wrist, the arm. Okay, and so we can do a procedure known as fMRI, functional magnetic resonance imaging. Okay, and what that does is when you think about moving your arm, actually, if you even watch me move my arm, the areas of your brain that control your arm will actually become active, okay? So for a patient that, for example, has a spinal cord injury, that patient can be placed into an fMRI, and you can say, think about bending your elbow. Think about opening and closing your hands. And you can look at what areas of the brain light up, okay? So that tells you what part of the brain is involved in, say, moving the hand or the wrist or so forth. Then what I can do is implant electrodes. So we've developed a set of electrodes that are about the size of my small fingernail here, and they sit on the surface of the brain, and they have 100 electrodes, and those electrodes will measure that electrical activity. So I know where in the brain is involved, say, in controlling the hand. Okay, I know that location. We'll place those electrodes in that location. All right, now there's actually a pedestal which is attached to the skull, which then a connector goes to. And that connector then takes all those signals from those electrodes, puts them into basically a box, which then processes them and amplifies them and so forth, so that a computer can begin to look at them. So basically takes them from analog signals into digital, okay? Then the computer can begin to process them. And then what the computer does is has to look at those signals and try to figure out what you wanted to do. So there has to be a training process involved where you ask the patient to try to do something, and they try to do it. You look at the activities, okay, the way the neurons are firing, and you do process basically is called decoding, which is you try to figure out from what the patient's trying to do and what you want them to do, how to basically interpret those signals. And so you do that initially on a set of trained tasks that start off with things very simple and then work to things that are more complex, okay? And you develop these decoding algorithms. And so now I know how to take that information and decode it. So now I can move past training and actually allow you to do things, okay? And so it becomes a very iterative process, okay? Because unlike an amputee, we don't know, for an amputee, we know that, the median nerve went to this location, and, because we know the physiology, and so we know if we tap into that nerve, that means, I'm moving my finger or so forth, okay? You don't have that kind of one-to-one correspondence in the brain, right? So we know the general area of the hand, but we don't know exactly, this neuron connected to this finger.
Do you think we will?
No, because there's a lot of other levels of processing that happen in the brain. So you move your hand, and those signals travel down through the brainstem, through the spinal cord, and so forth. And there's other processing that is not fully understood that goes on. Okay, so it's not the same kind of one-to-one correspondence. Okay, there's a concept known as plasticity, which is your brain is constantly remapping nerves. Okay, so for example, somebody that has a stroke. Okay, so what happens is there is either there's some interruption in blood flow, whether it be a clot or a bleed in the brain that causes death of some portion of the brain. So you actually have neurons that die, and so that's why somebody that's had a stroke will have various levels of impairment depending on where the stroke occurs. But if the stroke occurs in the motor areas, then the patient will lose some level of motor function depending upon where the stroke occurred. Okay, so what happens when somebody rehabilitates from a stroke? The therapist will take the patient's arm and actually say I've lost use of the arm, and they will take the arm and they will try to move your arm, and of course you can't do it, and they'll move your arm for you. Okay, and so what happens is through the visual system, looking at my arm moving, through whatever residual capability you have, the brain starts to be able to some level remap neurons so somebody can relearn how to use their arm. They're probably not going to be as good at it as they were originally. Some cases they're fully recovered depending upon the age and severity of the stroke and things of that nature. So it's very similar when somebody's learning how to use a brain-controlled prosthetic, that they initially will fumble around with it a little bit, but then the brain begins to at some level remap itself, and you learn how to more effectively control the arm. So it's really an amazing thing that we don't fully understand everything that happens, but it's very but the brain is very dynamic and will adapt itself as needed in order to figure out how to take the capability it has and reuse it in a different way, and that's exactly what happens. And so what we see over a course of several months, patients will their abilities will increase greatly as they it's like anything else, as they practice. Okay. Now what happens? So once we figured out we have to bend the elbow, for example, we actually then have to take those signals and we have to convert them into something that will actually make the prosthetics elbow bend. That's fairly straightforward. That's a kind of a classical kind of robotic control type of problem. Well, but what I have to have is an arm actually control. So if you think about everything you can do with your hand, all right, it's pretty amazing. Marvel of nature, right? All the things that you can do. And so what we want to do was to make a prosthetic that actually has the same dexterity, so it can do virtually everything I can do with my hand, and also with the same strength. Okay, so for example, the limb that we built can curl 45 to 50 pounds. Okay, which we joke is more than some of the people working on it can do, but you also want it, because it's a prosthetic, it's got to weigh the same. So you want dexterity, you want strength, and you want low weight, and you want it in a form factor that's similar to the human hand. So that means same size, same weight. Okay, so getting 2 out of 3 of those things is really easy. Okay, but getting all 3 together is really hard. Okay, because to get something, for example, fingers that can do a pinch of 20 pounds, to get enough torque in a motor that will fit into the size of my knuckle is something that didn't exist, and so we had to create that. And so we literally took motors that were probably the size of my entire finger and reduced them down to something that would fit into the knuckle. Okay, and so again, so when we think about the interdisciplinary nature of this, okay, a neuroscientist would normally never talk to somebody that develops miniaturized motor systems. Okay, and that's an example, kind of one of the things that we had to plug together. Okay, and kind of bridge that gap. Okay, so in the arm that we've developed, So each finger has its own motor to control it. So they're all, plus we have motors so that we can actually do what we call adduction, abduction. The only thing we can't do, if you're a Star Trek fan, you won't be able to do this. Okay, so you won't be able to give the Vulcan salute. But other than that, we can pretty much do everything. The thumb. Okay, you think about what you can do with your thumb. It's almost, your thumb is really a miniature version of your arm. Okay, it can move all these directions just like your arm can. So we have basically had to take everything that an arm could do and put it into a thumb. Okay, so we had to do all that. So if that wasn't hard enough, okay, what we also wanted to do was to provide sensory capability. Okay, so we wanted to put arrays of sensors on the fingertips, not just a single sensor, but arrays, because if I touch a surface and I roll my finger, okay, I sense that because of various pressures across my fingers, and it changes. So I want to be able to do the same type of thing. So we have arrays of these of approximately 15 to 20 sensors that actually sit on the fingertips that measure pressure. We also measure vibration, okay, because your cell phone rings or vibrates, okay. You want to be, or I run my hand across a rough surface. Vibration tells me something about the texture, okay. I want to measure heat flux, okay. So if I touch a cold surface versus a hot surface, I don't really have to worry about burning the arm, but it's useful to know, what the temperature of the surface is, okay. So I had to take all of that sensory capability, and we had to cram that all into the fingertips, as well as each motor can not only move, but it also measures its torque. It also measures its position. So if you close your eyes and you move, I say, touch your nose, you can do it, right? We can all do that, okay? And that's because we know where our hand is in space. That's called proprioception. And that's another goal, is we'd like to be able to do proprioception. So we want to know where all the joints are at every time, so we can figure that out. Now that's a lot of information, and we haven't learned yet how to use all that information. So we've taken the first steps of stimulating nerves and providing sensation, which have very dramatic results. Over the next years, we will learn much more about how to take all that sensory information and encode it. So we decoded from the brain, now we're going to encode, and there's another area of the brain called somatosensory cortex, in which is involved in sensory perception. And what we will next do is actually stimulate those areas of the brain. We've done it on peripheral nerve. Next step is actually to do that in the cortex. So we do essentially the reverse of the process, so that we provide this sense of sensation back to the patient. Okay, so a lot of different moving parts here, and each one of these things I've talked about, we have people that are highly, the world's experts in sensory perception, in motor control, making motors, making sensors. Okay. The other thing we had to do is, if you think about amputees, many amputees are transradial. Again, missing a hand and a wrist. And that's actually one of the more common forms of amputation. Okay, and it's not the whole arm. So not only did we need to do all those things to make the hand move and be able to feel, but we also had to be able to do all the processing. So all the smarts of the arm are actually located in the hand also, so that if we take away the rest of the arm, the hand can still function by itself. And so we crammed a lot of things into the hand in order to be able to give it the greatest level of functionality. We also made it highly modular, which means that if, say I break a finger, okay, I just undo a couple of screws, I pull the finger off, I put another one on, put the screws on, I'm back in business. Okay, so it's so I don't have to take the whole thing apart to fix it. So I can do. So actually, what we do now is, if one breaks in a lab, say in Pittsburgh or elsewhere, we say, okay, swap out the part, FedEx it back to us, FedEx them a new one, and they're back in business. And we do that overnight. So we can very rapidly change out the arm. Now, the other thing that we've done is the arm itself. You guess this is a research platform. It's very, very complex, and it's not a inexpensive item. Okay, so we have many people that would like to use arms, but we don't have a lot of them. So we have 5 of them. Okay, so we also have a virtual reality environment that we've developed. So we've taken everything I've talked about, and we've created a virtual reality environment. So now either the amputee or the person that has a brain implant can unplug from the real arm and plug in a virtual representation of the arm, and then they can actually manipulate that arm on a 3D monitor and interact with objects just like they were actually wearing the arm. So a researcher who's studying some aspect of this doesn't have to have all the hardware. They can develop everything in virtual space, okay? And then when they're ready to actually try it out on hardware, they're much better prepared. We also use it as a training tool. So for an amputee that for example, just had this targeted muscular reinnervation surgery, which is where we remap the nerves, okay? That takes about 6 to 9 months to recover. Nerves grow very slowly.
What was that called?
Targeted reinnervation, targeted muscular reinnervation.
And okay, that's the process of
yeah, so that's where you take a nerve that used to go, run down your hand, and you move it to, say, the chest muscle somewhere. Okay, and nerves grow very slowly, so it takes many months for that nerve to grow into that muscle tissue, so that when I think about moving that part of the limb, it'll actually contract the muscle. Okay, so that takes some time. And so, for example, what we can then do is send a virtual system home with the patient, and they can put some electrodes on, and they can practice with this, so that when they're ready to come into the laboratory to actually try out the real arm, they're ready to go. They've had a chance to practice it and develop their skill base, so they're not starting from a zero base.